Okay, so here is a video with some test hints for thermodynamics. So, first thing we're going to talk about is a Carnot engine. Then we're going to talk about thermal expansion. Okay, so let's talk about our Carnot engine. Well, first let's talk about the efficiency of a Carnot engine. It's a theoretical maximum efficiency given to you as that, where your temperature always needs to be in Kelvin, and this is the temperature of your hot reservoir and the temperature of your cold reservoir. Now, on a PV diagram, a Carnot engine looks something like this. Let's say we start at this point here. The first stage of the Carnot engine cycle is isothermic, meaning delta T is 0, which also means delta U is 0. Now, the next stage looks something like that. And that second step is adiabatic, meaning there is no heat flow. So if you look at this second step, my volume here increases, and we're going in this direction. So if my volume increased, that means that the system did work. So if we look back at delta U equals Q plus W, my system did work in this second step. So let's go A, B, C. So we're talking about B to C. It's adiabatic, so Q is 0. The system did work, which means the surroundings did negative work, which means delta U is also negative. In the second step of a Carnot engine cycle, I'm actually losing internal energy. So my temperature here, my delta T, would go down. Now, the third step comes back like that, and that third step is also isothermal. So let's call that D. So A to B, isothermal. B to C, adiabatic, no heat flow. C to D, because again we're going like this, C to D is isothermal. Then the last step, to get a complete cycle, I go back to A. Adiabatic, D to A is also adiabatic. So look at what's happening here. Isothermic means there's no change in temperature. Here there is no change in temperature. But B to C, my energy went down, which means temperature went down. So from here to here, I'm at a lower temperature for both of these because the temperature at D is the same as the temperature at C. But B is the same temperature as A, and the temperature at C is less than B, which means the temperature at D is less than A. So going from D back to A, my temperature increases. Because from B to C, I lost internal energy. From D to A, I've got to gain that energy back, because for a complete cycle, delta U is 0. So with a Carnot engine, this is your maximum efficiency. Remember, isothermic, adiabatic, isothermic, adiabatic. Okay, now let's talk about thermal expansion. With thermal expansion, the change in length is given to you as the original length times alpha times the change in temperature. This alpha is the linear expansion coefficient. And let's just say for a given material, let's just say it's 0.5, the units on it are Kelvin to the -1, because the units I need are meters. Well, this is meters times something times Kelvin. So I need kelvins to cancel, so I get the units like this. So let's just say I've got a rod and it's 10 meters long. And let's say it's got that linear expansion coefficient. And I up the temperature from 100 Kelvin I add heat to 200 Kelvin. Well, delta T would be 100 Kelvin. So delta L, or the change in length, would be 10, my original length, times my alpha, which is 0.5 Kelvin to the negative 1, times delta T, which would be 100. So half of 100 is 10. 10 times 10 is 100. Delta L would then be 100 meters. So the change in length would be at 100 meters, which is why that linear expansion coefficient is a ridiculously high coefficient. Heating something 100 degrees Kelvin isn't going to make it 10 times longer than the original length. But this would just be a hypothetical type of question. So there's your test hints. Watch the other video tutorials, study up, remember your training, and you'll be fine.